start anyway. So here we go. Let's try it again. Single take. We can do it. Let's go. What? Don't make me laugh. All right, here we go. I'm just making this shit up as I go along. Right. Hi, welcome to everyone's favourite segment, Mailbag. Let's get straight into it. This one is from Emmett L. Brown. No idea who Emmett L. Brown is. So let's give it a go. Everyone loves Mailbag. So, geez, not packed very well. What the hell? What a t-shirt we'll check out. And what the is this? It's a Microsoft Surface tablet with some young-looking dude on there doing a piece to camera. What the?
Hi, I'm Dave Jones. I was speaking to a colleague the other day and we were talking about video blogs.
Video blogs. Bloody no future in video blogging. What are you doing? There's absolutely no future in video blogging. That's crazy. Shut up. Shut up. Can't shut this guy up. Cannot shut this guy up. He is now shut up. Yes, April 4th, 2009. I was going to insert a joke about Doc Brown falling off a toilet, but David said that no one would get it. So, no, there is no falling off a toilet joke with Doc Brown. Anyway, this is the 1000th episode, and I thought we'd do a medley of stuff that people like, different segments. So, got to be brief. Let's get to it, shall we? Everyone loves a tutorial. So let's go. Yes, I set this up in 2009, whatever. What are we up to? It's number 1,000, but like whatever, 1,100 videos and something. Let's get to it. Come on. All right. Transistor as a clamp-in Zener. Here's one you may not have seen before. You probably won't find it in any textbook really, or pretty much information on this anywhere, but it's used in a product, and it's a bit of a naughty circuit. We're going to use transistors the way you shouldn't use them, but there's a reason for it, and it does actually work from a big name manufacturer. NPN, let's look at bipolar junction transistors, how we can turn those into a clamp-in Zener diode, a bipolar clamp-in Zener diode that can use in either direction to clamp impulses and overloads and ESD and all sorts of other stuff. So let's take a look at it. This is a configuration here, the two collectors joined, the two bases joined, and we've got emitters either side. It's really weird. They're both NPNs, but one's flipped up the other way. So you might think, how can this conduct? Well, we'll find out. Now, don't take a look at this. Let's go straight over to the equivalent circuit here. Base, collector, emitter of an NPN BJT, bipolar junction transistor. You probably won't see this configuration in your usual explanations of the equivalent circuit of a transistor, but because we're using it in a certain overload mode, it becomes relevant. There's actually a bipolar junction transistor can be modeled as basically two Zeners inside. There's one Zener from base to emitter. In fact, because it's forward biased like that, it's actually working as a diode, but it's in its reverse configuration. If you look at the data sheet, VEBO, or the voltage, sometimes called BR for breakdown, is the emitter base breakdown voltage. In reverse, it'll break down and act like a Zener at about 5 to 10 volts. I've done a whole video on Zener diodes. It's really cool, detailed, down below. Check it out. It's typically, for most BJTs, can be higher, but typically 5 to 10 volts. It's actually an avalanche breakdown. Anything under 5 volts is actually a Zener. I explained that in the other video, linked in down below. And base to collector, we've got what's called VCBO, and you'll usually find VEBO and VCBO in the absolute specs of a data sheet, like don't exceed these, magic smoke will escape, warn him, Will Robinson. So usually we don't want to operate, but today we are. We're going to be pretty naughty. So in the reverse configuration here, because of the construction of the BJT, it has a much higher Zener voltage, typically 20 to 100 volts, something like that, can be higher, but we'll run with these. So how does this work? Well, your base emitter junction like this, if you've got a positive voltage here and a negative voltage here, base emitter is just your diode drop. It's just a diode. It's a Zener diode, but in the full configuration. So 0.6 volts, near enough. Then our reverse, because we're actually using base, emitter base, positive, negative, it's acting like a Zener to give us a roughly, we'll call it 6 volt drop. So anything over 6.6 volts here will cause this to conduct and clamp. So if you've got a series resistor on the input, it clamps everything. Fantastic. And likewise in the other direction, negative and positive, bidirectional, 0.6 volts and 6 volts. So it'll clamp at plus minus 6.6 volts or thereabouts. Let's go to the bench and check it out. Come on. All right, here we go. Check out this. What we've got here is the same configuration that we had before. We've basically got our Zeners. I've got PN2222s, voltage Zener, input series resistor here, and the voltage of the supply input here, the voltage of the Zener across here, and the current flowing through the circuit here. So you can see that there's basically no, at 1 volt, for example, there's no current flowing through there, and it's just, it's as if this isn't there because it's not clamped yet. But as soon as we reach the threshold voltage, you'll notice that there's basically no current there, okay? But if we might start to conduct a little wee bit because these aren't great transistors, but let's take it up to 10 volts. Bingo, it clamps at 8.26 volts. And we can actually go up higher. Let's go up to 20 volts. It still clamps at 8.3 volts, and because it's bipolar, it works in the other direction. Negative. There we go. I just inverted the input voltage, minus 20 volts. It still clamps at 8.3. Fan-freaking-tastic. And these are quite fast clamps, great use for overloads. Now we can actually show the AC configuration of this. So let's plug it in. I've got a couple of diff probes here, don't really need it, not really high voltage, but check that out. We can see how one waveform, there we go, it's actually clamped it like that. And if we actually turn it down, there we go, if we actually turn it down like that, there's actually 2 waveforms in there, you'll see, because it's not clamped. So they're equal, but once you actually go up in voltage, then you'll find that it clamps. There we go, and we'll go up, you see it start to clamp. Fantastic. There you go. So it's a bidirectional clamp. I love it. So there you go. I hope you liked that short tutorial there. Now, it wouldn't be an EV Blog 1000th episode. Oh no, wait, no, I forgot. Geez, where's this thing used? Typically in Fluke multimeters. They use this circuit all the time. The classic Fluke 87 here. Check out this. I don't have my poker, but there is your couple of transistors down in there. So they actually use that for the Cat3 input clamping that you can see. We've got, okay, let's have a look at another one, the Fluke 3000 meter. Flip that open and over, and ta-da, check it out. This actually has 2 parallel configurations of those for extra power dissipation, but this is quite handy to use these. A very fast impulse clamping response, and used for the 1000 volt Cat3, which I believe is 8 kilovolt impulses. So it clamps those quite nicely, short, sharp. They're not high power dissipation, but they're okay. And you might reuse these elsewhere in your bill of materials. So very handy to reuse parts. So there you go. That's a common use for those. So I hope you enjoyed that tutorial. Now, let's get back. It wouldn't be a 1000 video if we didn't have a whole bunch of scopes. So what I'm going to do here, I'm actually generating, let's do a quick review comparison. I'm generating a 500 microvolt RMS signal, and we've got the classic Tektronix 2225 analog scope with 500 microvolt per division range, and there's the input signal. Now let's actually compare this. So we're comparing the noise across several different scopes. Now I've actually frozen and captured this. Let's have a look at Keysight 3000 here. You'll notice this is not a true 1 millivolt per division scope. So we're getting a whole bunch of horrible quantization noise on there. That is just absolutely awful. You wouldn't want to use this scope if you were doing low signal work at all. The Tektronix MDO 3000, this one is a real worry. Look at the amount of noise on there. look at it. You'll see that other scopes are much better. So this is only 1 millivolt per division minimum, but there's a lot. Oh, by the way, this is a 1 megahertz sine wave, and all the scopes are set to 20 megahertz bandwidth limit and the same memory depth of 1 meg. There's no averaging or anything else turned on. So yeah, the Tektronix MDO 3000, really noisy. I don't know where that's coming from. And you'll see that in the contrast of this Rohde & Schwarz RTB 2004. Check it out. This is 1 millivolt per division, and this is a 10-bit ADC. But look how nice that waveform is. Absolutely beautiful, low noise. Awesome work, Rohde & Schwarz. The HeyMeg one up here, 1 millivolt per division, and that one's got a little bit of noise on it, but otherwise a reasonably clean result on the HeyMeg / Rohde & Schwarz. The new Keysight 1000X series scope. This actually is supposed to have a better 1 millivolt range, but as you can see, it's very similar to the Tektronix. So there's a ton of noise on there. Not a great result at all. The Rigol 2000 series, let's have a look. Once again, there's some higher frequency stuff on there. This has supposedly no, it doesn't have a true 500 millivolt range, because you can see some quantization amplification on there. Like you can actually see, just not as bad as the Keysight, but still bad. Anyway, the Teledyne LaCroix, 1 millivolt per division, not a bad response there. Fairly clean waveform. Everyone's favorite, the Rigol 1054Z or not. It's a 1 millivolt per division range. Very, very noisy. Not the noisiest, as we'll see, but still not a great result. And then the new Siglent 1000X series supposedly has a true 500 microvolt per division range, and it's a pretty good result. Fairly clean. Look at that. You can see some noisy details on there, but that's an excellent, excellent result for low noise measurement with a true 500 microvolt range. And then, this GW Instec, this is the worst of the bunch. Look at that. That's just horrid. Blech. Like, let's just not even go there. And the O1, this one has a, the O1 has a 14-bit converter, but it's actually only 12 bits at the moment. And what we're looking at, this is 12-bit. The 8-bit is a little bit, it doesn't show the detail in there, but it's still pretty clean. So that's actually an excellent result on the O1. Very nice, but it's only got 1 millivolt per division. So there you go. That's just a quick comparison of all these different scopes. Hope you like that, and I'll leave that set up and do some more tests on that in the future. Now, everyone loves teardowns on the EV blog, and I've got something special. Let's check it out. Woohoo! You might have seen this on a previous video, which I'll link in down below, where I did the Channel 7 TV transmitter teardown. This is the 300 watt amplifier that transmitted the analog TV signal in Sydney for about 20 years. This one, 300 watts, as I said. This one was the preamplifier, a 300 watt preamplifier for the video signal, and also they used the same one, might have even been this one, for the audio. So the audio went out at 300 watts, the video went out at several hundred kilowatts. It's got a phase shift input here so that you can parallel these things up and tweak them for the same phase so that they load equally. But there's just an input, output, and overload indicator. So let's take a look inside this baby. And yes, we have the schematics. You ready for it? Oh yeah, the RF aficionados are wetting their pants right now. Look at this thing. Oh, I have to do a detailed teardown. This will be very short, but look at all the rigid coax lines here. Look at that, little stargates inside. Look, little rigid coax penetrators. Here's the power supply. It operates off 28 volts DC system supply. And let's take a look at the topology used in this thing, shall we? So I'll whack it up here like this, and I'll take you briefly through. Oh, by the way, I do have the schematic. I'll link it in down below for those playing along at home. Now, the input signal comes in down here, and it goes into a limiter circuit because you don't want some dickhead feeding in some input signal that then blows up your amplifier, and a couple of million people in Sydney can't watch their TV signal. So it just clips and limits the input signal so it doesn't damage anything else. And there's the phase adjust. Now it goes into a circulator, which I'll explain shortly, and then there's a couple of preamplifier transistors over here, and then that leads up into another circulator, which then goes into two circulators, which basically split the signal out like this into two separate channels. So there's actually two power amplifiers in here, two complete separate stages like this. I believe they do this for redundancy, so that if one blows, the other one still goes and they can't affect each other. It recombines in a circulator and then comes out down here. That's tapped off for an overload indicator display like that. Beautiful. Now, I promised to briefly mention circulators, so let's give that a go. Let's have a look at these circulators down here. What a circulator does, it's a passive device. It uses ferrites, and it basically does RF power protection. So it basically circulates the power through to a dummy load here. So if some idiot shorts the output of the antenna here, shorts the output, then what it will do is automatically dump all the energy into the load like this. The load is internal. Well, no, that might be external, but it dumps it into the load instead of blowing up your transistors over here. Very, very nice. And you can probably see the power resistor is going to be under there near the output circulators for combining. There you go. That is very, very nice bit of kit, and I'll have to do a more detailed teardown on that. So I hope you enjoyed that. Now, one that we all like on the EV blog, hopefully, is debunking. So let's have a look at a debunk, shall we? Ta-da! Right, which product is going to win the retarded product of the Century Award? Because Century's only 17 years old. So, well, there's a lot of contenders, isn't there? You know, Batterizer, Solar freaking Roadways, and all sorts of stuff. But this one, I think, takes the cake. The sheer number of the dollars that have been invested in this, and just the sheer ridiculousness of the idea. Let's take a look, shall we? The winner is, drum roll, uBeam. Now, if you haven't seen it, I've done a blog post 2 years ago debunking the uBeam concept, as have many others, including the former Vice President of Engineering at uBeam has even debunked it. This is how bad it is. Okay, now if you don't know what it is ultrasonic wireless power transfer. It's like Wi-Fi for charging. Woo, that gets all the investors juiced up, doesn't it? Yeah, it's going to be the energy infrastructure of the future. Oh, by the way, 28 million bucks they sucked out of the investors for this boondoggle. Unbelievable. They reckon it's safe. They reckon it can be used in buses, trains, planes, cafes, gyms, hotels, and stadiums. If we can sit in a stadium, if I had my phone, here it is, sit in a stadium and big, huge stadium, and your phone magically charges. What's that? Yeah, bullshit. Unbelievable. And it will power TVs without wires. You can sit TVs in the middle of the room and they just magically work. Woo! Pixie dust. Now, they were very secretive for a couple of years, and then they finally revealed some stats. They've been working on this for like 5 years, okay? And they finally said, oh, we can do a 4-meter radius, and we can charge a phone at 1.5 watts. Yeah, it's not nearly as good as USB can do, especially USB-C these days. You can wonder why anyone needs wireless charging at all, really, with how fast modern chargers can actually go. And they released their specs for what their transmit power is. 145 dB to 155 dB at 60 kilohertz SPL, sound pressure level. Now, we'll talk about that in a minute. Now, look, the power with ultrasound, in air, different mediums have different things. It drops off with a square of the distance, approximately, 3 dB per meter. Nice round number. That's actually what it kind of is in air. So even if you're 1 meter away, just with the air alone, no other losses, you lose 50%. It's only 50% efficient. And so at 2 meters, the efficiency is already 25% right off the bat before you start including, and that's assuming 100% efficient transducers, no nonlinearities, 100% focused. By the way, if they've got an array like this, it's actually slightly bigger, a bit bigger than this, then they can actually turn on only parts of it and get a smaller aperture size, and that will have a different natural focus distance. And I believe with roughly the size of the transmitter they've got, it's about maybe 1.5 meters guesstimate is the natural focus distance of that. It's beam forming as well, so they can do electronic beam forming to follow your phone. So they've got some very cool tech actually to locate where your phone is and then beam form. It's about a 1/2 second lag, which you can see in their video of following it. So granted, they've got some cool tech, but let's just look, actually let's not. This has to be short. I could go into the numbers here. 145 dB to 155 SPL is like, we can basically get, maybe my estimate at 1 meter, 2 meters, you can get that 1.5 watts. It's not a problem. And there's 2 ways to analyze this. One is with a continuous, a fixed transmit power, and the other one is with a variable transmit power where they change the size of that transmit aperture and pump more energy in to maintain 1.5 watts at every distance, for example. That's their figure. If they could charge quicker, they'd be boasting about it, but that's the best they could boast, 1.5 watts. It's getting down towards trickle charging, and it drops off with square distance, but it doesn't matter. This thing, no. It does not violate the law of physics, and yes, it does work. This thing can work. You can charge a mobile phone using ultrasound at several meters. It is possible, but the efficiency is down in the single-digit percentage, and in practice, it's going to be possibly sub 1% efficient because it's affected by temperature, pressure, which is altitude, humidity, there's nonlinear effects, there's saturation in the air because you're pumping in so much pressure, sound pressure level, the atoms, molecules just go, and they can't do it, like they just die, they saturate, poor little things, and you reach a saturation point. Anyway, there's obstacles like, I don't know, your hand's in the way, it's in your, or people walking past, all sorts of obstacles, and the receiver angle. Anyway, we could go through the result. It doesn't matter. The numbers do not matter with this. I'll show you a whole bunch of stuff on another whiteboard where I've got some major points that just blow this thing right out of the water. Let's go. And by the way, I'll link in a video of the CEO of uBeam. I challenge you to try and sit through all 15 minutes of it. It's really bad. Take it away, Meredith. It's the same whiteboard. It's the same whiteboard. Oh no. It's all right. Keep going. We're doing well. Oh, just cut it. And just pretend,
Kind of overheating in here.
Yeah, no, I thought you were. I thought I mentioned whiteboard and you were going to do it. It's all right. Here we go. Got framing? All right. This is why uBeam, it will never work, or any ultrasonic charging technology, why it's not practical. Let's go to number one, the efficiency. It's going to be bad. As I said, if it's 1%, I'll eat my tinfoil hat at 4 meters. Give me a break. It's the worst efficiency charging technology by an order of magnitude on the market. And remember, it's going to be very bad for the planet. If everyone implemented this, the planet would be screwed. Energy usage, energy consumption is one of the biggest problems we have on this planet. You might know of the Energy Star legislation, where it's actually against the law to sell products in some countries that aren't very efficient chargers, mobile phones and things like that. They need a certain standby power, they need a certain efficiency, otherwise you're not allowed to sell them. The MEPS regulations, all that sort of stuff. So right there off the bat, this thing shouldn't have even made it past the first concept. It's just the efficiency. Who's going to want this? It's just ridiculous for the planet. Unbelievable. Anyway, Cost. The cost. You need hundreds of these transducers that can do the 145 to 155 dB SPL in this thing, and for the transmitter, hundreds and hundreds of them, and you need maybe 100 of them for a phone size thing. If I've got my phone with me, we could have a phone sized device. We've got hundreds of, can you get my phone, David? Phone! We've got hundreds of, 100 roughly. Wave. There's David. We've got like 100 of these things on the back of a phone, and these are already sold in massive volume at for the automotive industry. They're several dollars each. Yeah, you might be able to pick them up on AliExpress for like 50 cents or something, but there's no way that Willy Wonka's transducer factory is going to churn out transducers of this capability and efficiency for anywhere near a practical consumer cost. It's just ridiculous. You need so many of them. And we'll compare that with the competition in a minute. Size. How thin can you make these things? Really, you can't. Look at their design. They've spent 5 years on this, tens of millions of dollars in development, and they've got a brick, a big brick, which you have to hold in a certain direction. Like, it's got to be flat on to the thing. There's a reason they hold it like that. Crazy. Nobody's going to want that. There's no way it's ever going to get thinner than a Qi charger that we'll look at. It's just right off the bat there, it's gone. And safety and legality. Let's have a look at that. On their website, it's all about safety, and but most countries actually have either legislation or recommended safe levels of 110 dB SPL. So uBeam is up to 3,000 times higher than what almost every country recommends as a safe limit for ultrasonics. It's ridiculous. Don't let them convince you otherwise on the website. It's just bullshit and waffle. Now, 5, and this is the face palm. This is where it should never have made it off the bloody napkin. You come up with the idea, ultrasonic phone charging. Okay, let's on the back of the napkin. Let's see how feasible this is. People put and use phones face up on a surface. So you've got all your receiver transducers on the back. In a cafe, which is one of their big usage scenarios, the thing's not going to charge at all. Zero. It's ridiculous. And people hold them in their hands at odd angles like that. Once you tilt it like that, you'll notice that they hold them in their demo perfectly like that with their fingers. Wow, of course it's going to work. But when people hold them like that at angles, and when it's their hands on the back, you've lost half your transducer area anyway. It's ridiculous. And people store them in their bloody pockets. Bloody modern huge phones, barely fits in my pocket. But they store them in their pockets, their bags, where it's absolutely useless. There is right there off the bat. It should not have been funded or made it off the back of a bloody napkin. It's just not a practical charging environment. And let's compare it with the competition, the Qi charger. My phone has a Qi charger already built in. Wireless charging, it's already built into a good lot of the phones on the market. It's called Qi, and it's already built in, and it's very efficient, upwards of 50% efficient. Pretty good, order of magnitude better than uBeam will ever be at its best. And it's cheap. You can buy one of the charging pads for $5 on eBay delivered to your home. Like, there is no competition. There's no way that Willy Wonka's transducer factory is going to churn out these things for anywhere near the cost of what the Qi charger and the thinness of a Qi charger with the coil in there, a tiny little slither of a coil, and just the controller charger chip to go with it. It's just, every one of these points is a showstopper. It's just dumbest idea ever. Anyway, that wins the retarded product of the century, decade, year, whatever. It's pretty dumb. Anyway, let's wrap it up. So that's it. That's 1,000 episodes. Hope you enjoyed it. That was pretty much done in a single take. And that was the idea, bit of a medley, or everyone's favourite segments. I could have done it in more detail. I'll play around with those scopes a bit more. That amplifier teardown is a bloody ripper. It's a Bobby Dazzler, so I need some more detail on that. But thank you for everyone who has supported me from day dot when I uploaded just a silly little idea I had for a video blog onto my personal YouTube channel, posted on Oz Electronics, and I don't know, I thought maybe 1,000 people would watch it, but I got 1,000 in the first week or two, and it's been growing. 2 years later, this, sitting in a lab, off the cuff, doing this sort of crap, is my full-time job, has been for 6 years. So thank you to everyone who's subscribed, viewed me. Some have viewed every video from day one. Awesome work. And everyone on the forum, and everyone, all my advertisers who've kept me financially afloat and all that sort of jazz. And yeah, this is probably video 998, officially numbered, and 1100. I don't know. I've done a crap load of videos. It's got 1,000 in the title. It's pretty official. So there you go. That wraps it up. Thank you very much, and hope you enjoyed it. Catch you next time.